It's SEM without reaching there.
Yes, correct. Exactly, in a nutshell, yep.
So if you have a package for those, you can technically do mediation as well.
Yeah, so we did that last week with Levon.
Oh, the law, oh, right.
Yeah, so like Levon is like a structural equation modeling package, and we can fit a mediation model in Levon if we wanted to, yep. So we can do all that stuff. All right, so I'm gonna jump in and talk about structural equation modeling and how to do it in R. So this particular lecture is just going to extend everything that Renata talked about, so we're gonna elaborate on some of her points so we better understand what structural equation modeling is. So I wanna talk about path models and also important terms, concepts, and symbols. And then I wanna walk through how we can actually do this in R with an example. So all of those steps that Renata talked about, I want to show how we can implement those in R and how we do those. Get this out of the way. So when you read about structural equation modeling or when you hear SEM in a lecture or a talk, what the heck does structural equation modeling mean? I perform structural equation modeling. What the heck does it mean? So structural equation modeling is not this kind of singular method or monolithic method. It's actually kind of an umbrella term that consists of a broad range of techniques and frameworks. One of those techniques is path analysis, which we're going to be talking about today. And then the other one is confirmatory factor analysis, which we'll touch upon briefly next week. And there's some other techniques too, like multiple regression, and then there's also like growth curve analysis and stuff here, but we're just gonna focus on path analysis for today and factor analysis for next week. And with structural equation modeling, we can test and quantify theory, so it's theoretical in nature. If you don't have theory guiding you, then you probably shouldn't be using structural equation modeling. It's a technique that allows us to model variables that exist. These are called manifest variables, and I'll define what that is in a couple slides. And then also variables that technically don't even exist. This is called latent factors. And surprise, it's something that you already know how to do. So if you know how to interpret regression, then you can do structural equation modeling, I swear. How I like to view structural equation modeling is regression on steroids, where we're not only fitting one regression at a time, right? So if we're fitting a multiple regression, we're just doing it, one time. Here, we're actually doing it simultaneously. So we're fitting 5, 6, 7, 8, 9 regression models all at the same time, simultaneously. And under the umbrella of structural equation modeling, we have a technique called path analysis, which Renata talked about, which basically allows us to model relationships between variables. And what's important to note here is that with path analysis, we're only looking at measured variables. And we kind of already did a path analysis last week when we looked at mediation. So what I have depicted here is just a path analysis. And last week, we looked at the relationship between Facebook usage and exam scores. And we hypothesized that that was mediated by study time, right? So if you remember, if you spend lots of time on Facebook or TikTok or Instagram, you're gonna spend less time studying, and then that should lead to poorer exam scores, right? But what's important to note here is that this is a very simple example. With path analysis or structural equation modeling, we could fit lots of complicated models and look at lots of complicated relationships between variables. So this is just a simplified version of this. So what I wanted to do is talk about important terms, concepts, and symbols in order to understand structural equation modeling or path analysis. There's lots of terms that we should know. So an important distinction that we have to make within the SEM world is between exogenous variables and endogenous variables. So this is a picture of a somewhat complicated path analysis, right? So how I like to think about exogenous variables are basically as independent variables in your regression model. And when we look at this path analysis here, what we'll see is exogenous variables have arrows pointing out of them, as we can see here, but there's no arrows pointing into them. So that's an important distinction. And these arrows that are pointing out of the variables are causal or directional in nature. So they're thought to cause something. Each exogenous variable has a variance, which is measurement error. And this is really why a lot of people like structural equation modeling or path analysis, is because we can model this measurement error, which we can't do in a regular regression model. In a regular regression model, this measurement error is thought to not exist. But within structural equation modeling, we can model the error of that exogenous variable, which makes it really, really enticing. So exogenous variables are also allowed to covary with one another. And by default, exogenous variables are meant to correlate with one another. So when I say covariance, I just mean correlate with one another if we're talking about it in a standardized sense. So for example, X1 and X2 are allowed to correlate with one another. And by default, the programs usually allow them to correlate with one another. We can contrast exogenous variables with endogenous variables. So endogenous variables are synonymous or can be thought of as dependent variables in your regression model. And in a path model, what we see is that we have arrows pointing into those boxes, right? So they're thought to be caused by the exogenous variables. And I like to think of endogenous variables as basically having an error term, and we call this error term a disturbance. But this is basically just a residual in our regression model, right? So if you remember the regression equation, right, there's a residual term. Endogenous variables always have what's called a disturbance. So you'll hear that a lot in the literature, but that's basically just a residual term here. So the TLDR, exogenous variables, no arrows pointed at it, and endogenous variables have arrows pointed at it. How I like to remember these things, because it can get quite confusing, is looking at the prefixes. So we have EX here, so that means that it's exiting. And then EN or END means that it's ending up somewhere. So the arrow is ending up at that particular box. And as Renata pointed out, you can have a variable that's both exogenous and endogenous. So we can see in this particular example here, X3 has an arrow pointed to it, but it also has an arrow leaving it. So you can have both. So another important distinction in the SEM world is between manifest variables and latent variables. So in a path analysis, all we have are measured variables, or observed variables, or manifest variables. They're all synonymous with the same thing. And what we'll see is squares. That represents our manifest or our observed variable. And how I like to think about manifest variables is if you open up a data set, there'll be columns in that data set. Those column names are our manifest variables or our observed variables. And these take on certain values, and they could be continuous in nature, they could be ordinal, or they could be categorical. And we contrast manifest variables with latent variables. So latent variables in structural equation modeling represent latent factors, and these are represented by circles in the model, as is depicted here, and then also in Renata's example. So these are things, and I hate to say it, that technically don't exist. They're abstract phenomena, they're constructs. Sometimes we'll call them factors. And we're trying to model these. And if we go back to our data set example, when we open up our data set, there won't be a column for these latent factors or these latent constructs. So no columns. Instead, what we do is we take our measured variables that are in the data set, and we use these as a proxy for our latent construct. So I have an example here where we have things like attentional control, working memory capacity, and fluid intelligence. These are made up of measured variables. So attentional control is made up of anti-saccade performance, selective visual arrays performance, and the adaptive flanker. Working memory capacity is made up of symmetry span, rotation span, and O span here. And then fluid intelligence is made up of Raven's advanced matrices, letter sets, and number series, right? So all these measured variables serve as a proxy or kind of indirectly represent those variables. And then the beauty of structural equation modeling is we can test the relationships between these variables here, as denoted by the arrows. So just to remember, exogenous variables are going to be our independent variables, and endogenous variables are going to be our dependent variables. And I've kind of made that relationship clear here, where we have our regression equation, and then we have our kind of path analysis, structural equation modeling equation here. So we also need to know about variances, covariances, and disturbances, because those are important in the SEM world. So a variance is represented by a double-headed arrow, usually to itself. Covariances are also represented by double-headed arrows, but usually it's to another variable. So as I have depicted here, we have this double-headed arrow going from X1 to X2. And these are not unidirectional, they're bidirectional. And again, this just represents a correlation between these two variables. So what does it mean to covary with another variable? It means that there's shared overlap in the variance, as is depicted here. But the beauty of structural equation modeling, of path modeling, they don't have to correlate with one another. Maybe you have strong theory that suggests that x1 and x2 are not correlated with one another. What's cool is we can actually just set this correlation to 0, as I'm depicting here, and that means that there's no shared variance between those two variables there. We also have disturbances, and each endogenous variable in our model has a disturbance. And as I said before, a disturbance is just a residual in our regression model. And it basically represents kind of the unexplained variance. So it represents the influence of factors not included in the model, and basically it's just error. So here's a legend of important symbols in the structural equation modeling world that we went over. So we went over circles as latent variables. We went over squares as observed or manifest variables. One symbol we didn't go over is this intercept or triangle term. We're just going to put that to the side. We also have arrows as paths, and then we have our double-headed arrow, which is a variance or covariance. So in a path model here, right, we have measured variables denoted by these squares, right? So what do these arrows represent actually? So these arrows that I'm drawing here are actually our regression coefficients. So these are our B weights if we're talking about a non-standardized solution. But if we're talking about a standardized solution, we're talking about the beta, right? So big B here. That's what these paths represent essentially, regression coefficients. And when we're talking about double-headed arrows or covariances, when it's non-standardized, we refer to these as covariance. And when it's standardized, we refer to these as correlations. And it's quite common when we are describing these type of models to talk about these in standardized units. So it's kind of rare to have it's kind of rare to talk about these in unstandardized metrics. So when you're fitting these models, you should try to standardize your coefficients just to make interpretability a little easier. Questions so far? Lots of symbols, concepts, terms. So I have a little cheat sheet here that has some common terms and symbols. So if you're going to be doing structural equation modeling sometime in your life and you want to refer back to this, there's a whole list of terms and also what these symbols mean. And I've also linked to a post or a website by David Kenny, who talks about the basics of structural equation modeling. And I think he does a really good job introducing these terms and explaining structural equation modeling. So I definitely recommend looking at that website if you have any questions about SEM. So in the beginning, I said that in the beginning, I said that structural equation modeling is kind of regression on steroids, right? So basically what we're doing is we're taking each endogenous variable and we're regressing it on all exogenous variables that lead to it or are connected to it in a chain. So in this example here, we have 1, 2, 3, 4 endogenous variables. So from this, we can construct 4 regression models. So the first regression model that we could construct looks at x1 predicting x3, right? Because there's one arrow pointed to it. The second regression model that we could construct looks at x1 and x2 predicting x4, and that's because there's 2 arrows pointing to it. The third regression model that we can construct looks at x2 predicting x5 because there's 1 arrow pointing to it. And then lastly, we can construct a regression model that looks at x3, x4, and x5 predicting y, right? So what we're doing in structural equation modeling or path modeling is specifying all of these regressions and then running them simultaneously. And again, that's why it's important to know which variables are endogenous in your path model and which variables are exogenous in your path model. And we need to specify each of those individually. All right, so a very important term in structural equation modeling world is identification. So I wanted to spend a little bit of time talking about identification. So as I said before, structural equation modeling is highly versatile. We can fit lots of models and look at lots of different relationships between variables. However, we can't test every single model that we want. The model needs to be identified. And what that means is that there's a unique solution for all of the parameters that we're trying to estimate in our model. So how is this determined? Well, we have to figure out how many known values we have in our model and free parameters. And this is called the minimum condition of identification. How I like to think of this is as money in the bank. So if you want to purchase something, in order to purchase that thing, you have to have the exact amount of that thing, or you have to have a little bit more money in your bank account, right? So this is the minimum condition of identification. So you might be wondering, what are free parameters and what are known? How do we determine those things? Well, first, free parameters are all regression paths, covariances, variances, and disturbances in your model. That's what constitutes free parameters here. So it's every one of these double-headed arrows, or excuse me, every one of these single-headed arrows. Those are our regression paths. All of the disturbances that we have, so these D parameters, encased by the circle here. Covariances between variables, so if there's these double-headed arrows, and then also all error that's associated with these exogenous variables here. That's what I mean when I say free parameters. And then the known values in our model can be determined by this equation here, where k is the number of measured variables. So we could just do k times k plus 1 divided by 2, and that gives us the known values in our model here. And we determine identification by calculating model degrees of freedom, and this is just the amount of additional things we can estimate. And we can determine this by taking our known values and then just subtracting the free parameters, and we can get our degrees of freedom. And if our degrees of freedom are greater than or equal to 1, then we can analyze our model. This is called an over-identified model. And in structural equation modeling world, we want an over-identified model. So this is what we always strive for. If our degrees of freedom are equal to 0, we have a saturated or just identified model. And here we can still analyze our model, but it's going to fit the data perfectly. So when we talk about the covariance variance matrix, it's going to basically be able to reproduce that perfectly. So there's going to be no fit indices. We can't compare models when we have degrees of freedom equal to 0. And as an example of a saturated or just identified model, we can think of multiple regressions that we fit. Those have as many knowns as free parameters in the model. So if we subtract those, we're going to get 0. Then we can have cases where the degrees of freedom is less than 0. And this means that we have an under-identified model. And this is something that we don't want because we can't analyze our model. We can't perform a structural equation model if our degrees of freedom are less than 0. So this is a case where we have fewer knowns than the parameters we're trying to estimate, right? So if you overdraft your bank account, your bank is not going to allow you to purchase that thing that you want to purchase. So to make this a little bit more concrete, I like to use mathematical examples or mathematical analogies. So let's take these two equations here, 10 equals 2x plus y and 2 equals x minus y here. So here we have 2 knowns and 2 unknowns, right? So 10 and 2, and then x and y. There's only one set of values that can solve this equation, right? No other values are going to be able to solve this equation. So we can't test any other models because there's only 2 values that work here. This is an example of a just identified case. Let's look at another equation here. So 10 equals x plus y. There's one known value here, 10, and 2 unknowns, x and y. So there's an infinite number of solutions here, right, for x and y. So there's no way to derive a solution. So this is an under-identified case where we have fewer knowns than free parameters here that we're trying to estimate. And we can't analyze this particular equation in structural equation modeling. Now let's go ahead and take our first set of equations and add an additional one here. Let's say 5 equals x plus 2y. Here, we can try different values for x and y. So we can try 4 and 2, and we get 10 and 2, but it doesn't quite fit the last equation. We can try x equals 3 and y equals 1. We can see that doesn't quite fit the first equation. And then we could try 5 and 0, and we can see here that it doesn't quite fit the second equation. What's important here is that we're able to fit approximate solutions to these 3 equations, right? We can test different numbers and we might get different solutions here. So these are imperfect solutions, but this lies at the heart of structural equation modeling. We want to be able to test different models, right? We want to see which model fits the data the best, right? And we can't evaluate fit without alternatives, right? So this is a case of over-identification, and this is why over-identification is so important in structural equation models, because we want to be able to compare different models to one another and see which one is the best. So how many of you are familiar with the Saw franchise? Anyone? Jigsaw? No? Isn't any horror fans? Okay. So we're going to play a little game here, and you have 3 minutes. And unfortunately, if you don't solve it in under 3 minutes, something bad's going to happen. No, I'm just kidding. Sorry, you only get that if you've seen the Saw movies. But what I want you to do is I want you to determine the number of degrees of freedom from this path model here. So what's in the actual squares doesn't matter. But what you need to know, what you need to figure out is the number of knowns and the number of free parameters you're trying to estimate here. So I'll give you 3 minutes to do this so you can work with partners if you want to, or work alone. And then I'll walk through how we can estimate the degrees of freedom for this type of model. So was anyone able to get the degrees of freedom? Are they brave and adventurous to tell me what the degrees of freedom might be?
Well, we know that the knowns 10.
Yeah. How did you get the knowns?
With the number of measured variables plus 1 times itself.
Yep. Yep. So that's how we get the knowns in our model, which is 10, right? What about the free parameters? So I like to break this up in terms of like, so look at the regression paths, then look at the covariances, the variances, and disturbances. Do you know how many?
We were trying to figure out how to
Okay.
those 4 regression paths.
Yeah. So there's 4 regression paths, right? Okay. So what about covariances? So it's not modeled explicitly, so it would just be, so covariances are usually on exogenous variables, right? So there's how many exogenous variables are in this model, first off? So in this particular example, there's two exogenous variables, right? So they have no arrows pointing into them. So that's Q2 and Q12. So we could let them covary, but in this particular model, we're not going to let them covary, right? So we could say that there's zero covariances. What about measurement error terms here? So again, error terms are on the exogenous variables. So how many error terms would we have here? Two, yeah. So two error terms here. And then what about disturbances? So remember what type of variables get disturbances? There's two. Do you remember what type of variables get disturbances though? Yeah, so the endogenous variable. So if you have arrows pointing into it, then you get a disturbance because you're technically a dependent variable.
Q4 counts only as an endogenous, even though it has zeros going in and out.
Yeah, so you have, so since it has an arrow, so exogenous variables, you'll never see you'll never see an arrow pointing into it essentially. I mean, technically you can, but you can't have a disturbance and an error associated with it. So since this arrows are pointing into this particular variable, we'll give it a disturbance, or we give it a, yeah, because it has an arrow pointing into it. And then this one would also be a disturbance, right? Because you have an arrow pointing into it. So a particular variable would never have a disturbance and then also measurement error into it, so, or double errors. So the number of free parameters that we see here are 4, 5, 6, so we have 8, right? So how many degrees of freedom do we have? 2. So is our model identified here? Yeah, right? What type of identified is it? Is it over-identified, under-identified, just identified? Yeah, so it's over-identified, right? So if our degrees of freedom is greater than 0, then we have an over-identified model, which is what we want, right? And you can see that we left out paths here, right? That's the spirit of structural equation modeling. So we could have modeled something like this, right? We could have put a direct path here. We could have put some covariances here, but we're not modeling everything. So that highlights structural equation modeling, right? We're not modeling everything. This is not just a simple multiple regression model here. All right. So are there any questions about identification? So it's not simple, but I just wanted you guys to have a little fun figuring out the different paths. When I was in a structural equation modeling class, we got to do that all the time. So, but I thought it would be a fun little activity. So now what I want to do is I want to highlight the steps that we have to take when we're performing a structural equation model or a path model. And there's 5 steps, and Renata, I think, nicely kind of introduced those steps. So in step 1, we need to specify our model, which involves thinking about how our variables are related to one another, right? So what are the hypothesized relationships? Also, what are the endogenous and exogenous variables? What are the mediators? What are the moderators? What's the model code? In the second step, we need to identify our model. So we need to make sure that our model is over-identified. So we need degrees of freedom greater than 0. We then need to estimate our model. So I'm going to show you how we can estimate our model using Lavon and R. And we're going to be using maximum likelihood estimation, but there's also other types of estimation as well. But we've used maximum likelihood estimation before, so we're going to continue to use it. In the fourth step, we're going to evaluate our model. So do we have a good model fit? So I'm going to go over some fit indices that we can use that will tell us if our model is a good fit. And then lastly, if our model fits poorly, how can we improve our model? So these are the steps I want to walk through. And to highlight that, I'm going to use a data set that has several variables that predict intentions to apply to grad school, and then also if you actually apply to grad school. So when we load in this data set here, we have 5 different variables that we're going to look at. So we're going to have 2 endogenous variables, which is intent to apply. So do you want to apply to grad school? and then if you actually applied to grad school. And then we're going to also look at 3 exogenous variables: perceived value, so these are attitudes towards grad school; external pressure, so what is your mom, what is your dad, what is your best friend saying about grad school? This is normative beliefs. And then also perceived control over admission. So if you think that you're going to get into Princeton, how likely is it that you're going to apply to get into Princeton, right? So these are the variables that we're going to look at. And again, if you want to follow along, you can just download, or you can load into this data set here. So in terms of model specification, this is how we're going to basically fit the model. This is our model specification here. In this particular example, we have 5 direct paths, right? So we have 1 regression model, 2, 3, 4, and 5. So we have 5 direct paths here. We're going to look at the relationship between perceived value predicting intentions to apply, external pressure predicting intentions to apply, and perceived control predicting intentions to apply. Also intentions to apply and how that predicts actually applying to grad school. And then also perceived control predicting applying to grad school here. We have 3 indirect effects. So we're going to look at perceived value and applying to grad school through intentions. We're going to look at external pressure predicting applying to grad school through intentions, and then perceived control predicting applying to grad school through intentions. So 3 indirect effects. And then we also have 3 covariances here. So we're going to look at the correlation between perceived value and external pressure and perceived control, and then perceived value to perceived control here. And if you are a social psychologist or you're familiar with health psychology theory, basically what we're testing here is the theory of planned behavior. And the theory of planned behavior pretty much says that things like attitudes, external pressure, and actual behavior are mediated by intentions. So attitudes and external pressure influence intentions, and intentions influence actually applying to grad school. The theory of planned behavior suggests that perceived control, so if you think you're going to get into a place, can actually affect behavior, which is the addition of, this addition is the theory of planned behavior. This is an extension of the theory of reasoned action. But what I really think is so cool about structural equation modeling is that we can test models like this and see if they're valid. Okay. So as a data screening step, what I usually like to do is look at the correlations between these variables. So I think that this is a very cool graph. This is just kind of like a network analysis, looking at all the different correlations between the variables. And what I want to highlight here is that the correlations between these variables are moderate to high, right? With the greatest or strongest correlation being perceived value and intentions to apply. Sorry, these circles are not big enough to actually have the whole text. I haven't figured out how to actually make the circles bigger, so I apologize for that. Maybe one day I will figure out how to actually make them bigger. But again, we see that this is the strongest correlation, and we also see moderate correlations between the other variables here too. Yeah.
In this case, we are not using any latent variable, right?
No latent variables, just all measured variables. So next week when we talk about factor analysis, that's when we'll bring in the latent variables. Yeah. So given the moderate to high correlations between these variables, I think that the covariance between perceived value and external pressure and perceived control and perceived value to perceived control makes sense, right? These variables are correlated with one another, so we should allow them to covary. In the next step, we have to make sure that our model is identified. So as we already went over, the known equation is k times k plus 1 divided by 2. So here we have 5 measured variables. So we can just do 5 times 6 divided by 2, and that's 15. And then we need to calculate our free parameters here. So we have 5 regression paths, right? 1, 2, 3, 4, and 5, right? We have 3 covariances, right? So from perceived value to external pressure, and external pressure to perceived control, and perceived value to perceived control. So those are our 3 covariances. We have 3 variances. So we have 1 variance for perceived control, 1 variance for external pressure, and then 1 variance for perceived control. And then we have 2 disturbances. We have one on intention to apply, and then we have one on applying to grad school, because those are our endogenous variables in our model. So the degrees of freedom is the number of knowns minus the free parameters, which is 15 minus 3. So we have 2 degrees of freedom. So our model is identified. So we can proceed on and fit our model now. So to fit our structural equation model, we're going to be using Lavon. And I already introduced Lavon last week. And kind of a pain in Lavon is that you have to specify every single part of the path explicitly. So we need to declare equations for every endogenous variable in our model, right? So we can use the tilde symbol, and that indicates a regression. And we also need to declare indirect and covariances as well. So the colon equal sign declares a variable, so you can specify an indirect effect. The asterisk allows you to label a variable and name it whatever you like. The double tilde indicates a covariance or correlation between variables. And then next week, we'll kind of touch upon this, but if we want to specify a latent factor, we have to use the equal tilde sign. So how this is usually represented, so if we have a latent factor, let's say our latent factor is ham, and then ham has some measured variables that make up, the essence of ham. So we would use this equals tilde sign here, and then maybe we have 3 questions about ham in our data set, right? So like x1, sorry, that doesn't look like an x, x2 plus x3, right? So this is how we would specify a latent construct in the Lavon syntax here, where we're taking these measured variables and saying it serves as a proxy or a stand-in for ham. So we'll talk a little bit about that next week. All right, so we need to specify our model before we input it into Lavon. So that's what I have highlighted here. So this should look very familiar to you because we did it last week. But I'm still going to go through each line of the code and relate it to the path model that we're trying to fit. So the first line here is our first regression. And this regression is going to be all of the paths to intentions to apply. So I've labeled these things A, B, and C. So let's go back to our model here. And let's just label these paths here. So this is going to be A. This is going to be B. This is going to be C, this is going to be D, and this is going to be E here. So the first regression model that we're fitting is basically perceived value, external pressure, and perceived control predicting intentions to apply. That's our first regression model. The second regression model here is going to be all of the arrows to application behavior. So I've labeled these things D and E. So let's go back and look at our path model here. So we see that intentions to apply, predicting, actually applying to grad school is labeled as D. And then we see that perceived control has a direct effect on applying to grad school. That's E. That's our second regression model. Now we're going to specify our 3 indirect effects. So we have value through intentions, which is just A times D. So we learned how to specify indirect effects last week. But what we're doing is we're taking this path here, perceived value, and then multiplying it by D. The second indirect effect we're going to look at is B times D, which is external pressure, that path to intentions, and then the path from intentions to actually applying, which is D. And then the third indirect effect is perceived control to intentions, which is the C path, and then the intentions to apply to actually applying, which is the D path here. So those are our 3 indirect effects. And then next, we have to specify our covariances or correlations. And I said that we use these tilde or double tilde symbols. And basically, we don't need to label these. We could just put them directly in as our column labels. So we could do perceived control is correlated with perceived value. And then perceived control is correlated with external pressure. And then external pressure is correlated with perceived value. So that's how we would specify the model that we have drawn out here. That's why it's critical that when we're approaching this, we need to basically draw out a path model for us so we can label things and know what we're interested in. So once we have this model specified, then we can use our SEM function. We just put in the string that we created with all of our regressions and indirect effects and covariances, and then we can use bootstrap sampling here. So similar to last week. But before we look at the output, I want to talk a little bit about model fit. So we need to make sure that our model fits the data. And as Renato already stated, the covariance matrix is sufficient statistics for structural equation modeling. You don't even need your actual data to run the structural equation model. You can just input a covariance matrix and run the structural equation model like that. But ideally what we want to do is we want to do a comparison between the observed covariance matrix, so this is our sample covariance matrix, so our data set, and we want to compare that to our model-based covariance matrix or the predicted model that we've specified. And we just want to know if it fits the data well. So what does it mean if we have a good fit? That means that we're able to capture the bulk of relations between the variables in our model, and there's not a lot of covariance left over, so we didn't miss anything. So this means that we compare the relationships we've modeled to all of the possible relationships in our sample data. And you might be wondering, well, how do we do that? Well, thankfully, there is a whole host of fit indices that we can use to determine if our model fits the data. So this is only a handful of the fit indices that we can use to determine if our model is a good fit. So in one of the first programs to fit structural equation modeling called Lizroll, there are probably pages and pages of fit indices that you can use to determine if your model is a good fit. So we're not going to do that. Instead, we are going to use the Klein recommendations, and we are going to look at several of the fit indices. And this is what I want you guys to report if you're reporting structural equation modeling. And that's this chi-square statistic, RMSEA, which is the root mean square error of approximation, the SRMR, which is the standardized root mean square residual, and then the CFI, which is the comparative fit index. Sometimes the TLI is also reported, which is the Tucker-Lewis index. But these are the kind of the minimum that you should report. And luckily, Hugh and Bentler in 1999 came out with some cutoffs to determine if our model is a good fit. So they recommended that our chi-square statistic be greater than 0.05, so it shouldn't be statistically significant. The TLI should be greater than or equal to 0.95, and the CFI should be greater than or equal to 0.9. And then the RMSEA and the SRMR should be less than 0.08. When we look at these fit indices, we want to make sure that our model fits these cutoffs. So the fit indices fall into three broad categories. So we have absolute fit indices, and this measures how well our data fits the specified model. So the covariance matrix that our model predicts versus the sample covariance matrix. So we use the chi-square statistic, but if you have really large sample sizes, then the chi-square statistic is always going to be significant. So it's recommended that you use other statistics along with the chi-square. The SRMR is also an absolute fit statistic. And then this is the standardized difference between our sample covariance matrix and our model-based covariance matrix. And we want this to be as small as possible. We don't want there to be misfit or large misfit. We have badness of fit indices like the RMSEA, which measures how much worse the data fits the model from the just identified model. And then we have relative goodness of fit, like the CFI or the TLI. And this measures how much better the model fits than the null model. So this is where there's no relationships between the variables. And here we want the CFI or TLI to be as large as possible, preferably close to 1. So how do we get these from our output? So we can fit our model, and then we can use the summary function here to output the results. So here we're going to get standardized variables. So we're just going to set standardized to true. And then we're going to say fit measures equals true as well. So we're going to take this argument and set it to true. And this gives us our fit indices. So this is the outputted model here. So at the top, we have our estimator. So this is the estimator that's used, which is maximum likelihood. We have the number of total parameters in our model and then the number of observations, so 60. The model test user model is the chi-square test. And this is what we want to report in papers. So we see here that the test statistic is 0.86 and the degrees of freedom is 2, which we calculated. So our model is over-identified. And then the p-value here is not statistically significant. So is this a good thing or a bad thing? If the chi-square statistic is not statistically significant, is that good or bad? It's good. You don't need to have hesitation. Yeah, no, it's good. We don't want this to be statistically significant. The model test, a baseline model, is basically a model where there are no relationships between the variables. Here, the p-value is statistically significant, but we don't really care about this. We use this in comparison to our model or our path that we specified. And we can compare the model that we specified against the baseline model, and then we can get the CFI and TLI statistics, and these are 1. So is that a good thing or a bad thing? That both of these are 1. In the TLI case, it's over 1. Yeah, that's good, right? We want this to be as close to 1 as possible, so that's good. We're going to gloss over AIC and BIC. We have the root mean square error of approximation. That's 0. And then we also get confidence intervals, and we also get p-values. And ideally, we want these p-values here to be not statistically significant. But in terms of just the RMSEA of 0, is that good or bad? Yeah, that's good. We want it to be less than 0.08. And then we have the standardized root mean square residual, the SRMR, and that's 0.02. Is that good or bad? It's good. So our model fits the data pretty well, so we can proceed on. So this is kind of a messy version of the parameter estimates, so I'm not going to go over those just yet. But what I wanted to point out is that when we say standardized equals true, we have a column appended to our output called standardize all. This is what we would want to report in our papers. This is the standardized output. We don't have any latent variables, but if we did have latent variables, that's what the standardized latent variable column would indicate here. But for our purposes, we should look at the standardize all column here. So it's a lot to remember, right? Lots of fit indices, lots of cutoffs, but luckily Easy Stats has our back. So there's a function called interpret, and we just fit the model, the Lavon model that we have, and we run it. And basically it outputs all of the fit indices, the thresholds or accepted thresholds, and it tells us if it's satisfactory or not. So this helps a lot, right? So we can just put in our model and it's going to tell us if our model is good or not. And then we also have report performance. So we put in our Lavon model, and it's going to output some standardized text that we can then copy and paste into our paper. Obviously, it outputs all of these different fit indices. We would have to, choose the ones that we want to report, right? So like the chi-square and the RMSEA and the TLI. So those are the things that we would kind of extract from this. So this helps a lot. So this is the cleaned up coefficients, and these are all standardized. I use the model parameters function to just clean this up a little bit. But what we see here are regression parameters and whether they're statistically significant or not. So what we see here is that perceived value predicts intentions to apply. We don't see a significant relationship between external pressure or perceived control. Those are not statistically significant. We do see a statistically significant relationship between intentions to apply and actual behavior. And we see a significant relationship between perceived control and application behavior, right? So these are just our regression models. And then we also defined indirect effects. And the only indirect effect that we see here is value through intentions. So perceived value affects behavior through intentions, which would be predicted by the theory of planned behavior. So when reporting structural equation models or path models, we want to have a figure that highlights our model, right? But what we also want is to describe our model fit. So I have an example right up here. So the model appeared to have a good fit. We have our chi-square statistic, the SRMR, the RMSEA, and the CFI. So this is an example how you write that up. And then we'd also want to describe the significance of our regression coefficients. So I have a sample right up here. So the perceived value of graduate education predicted intentions to apply to grad school, but intentions to apply to grad school were not statistically predicted by external pressure to go to grad school or perceived control over the outcome of graduate admissions. However, intention to go to grad school significantly predicted actually applying, and so did perceived control over the outcome. Intentions to apply to grad school mediated the relationship between perceived value and actually applying to grad school. So this is an example of how you would write up the regression part of your model. This is just a visualization of our model with the standardized coefficients. And with SEMplot, which I think some of you used on your mediation lab, and I think I highlighted last week, you can kind of in a semi-automatic way, construct a path model. But there is some modifications that you have to do, like, specifying the locations of the boxes and then also the labels. But I think that this looks like a decent path model. It looks pretty nice. I don't know if I would put it in a paper like this, but for our purposes, I think it looks pretty good. All right, so our model fits the data pretty well, but there could be cases where the actual fit is not that good, right? So the fit is not satisfactory. So what can we do about that? So there's these things called modification indices or mod indices. And essentially there's unmodeled things that we didn't explicitly model in our model, right? So what modification indices tell us is basically all of the things we didn't model and how much better our model would be if we modeled those relationships and those paths. And what it tells us is the change in chi-square by including those relationships or paths. So basically these mod indices make our model better. So there's some controversy surrounding these mod indices because hopefully you can see that this has a potential for harking, which is hypothesizing after the results are known, right? So taking these relationships and putting them into our model to make the model fit better, it's kind of shady. So I think you can use these things, but you need to be transparent about it. So you need to say in your papers that you use mod indices, and the inclusion of these things should be theoretically guided. So as we'll see, sometimes the actual paths that we didn't include are actually pretty nonsensical, and we wouldn't include those in there. So we have to be careful about including these things. So what we can do is we can use the modifications indices function from Lavon, and this will tell us everything we didn't model. And we can see things like intent to apply correlated with application behavior, intention to apply regressed on application behavior, which doesn't make sense, right? Because we're going in the opposite direction. If you applied, how does that, predict intentions to apply? So some of these things are nonsensical, but it will report them. And what we want to do is we want to look at this MI column here, and this will tell us the change in chi-square by including that relationship or that path in our model. And what we usually look for is an MI of greater than 3.84. So if we include that particular path in the model, then that's associated with a statistically significant chi-square test. So that'll improve our model greatly. I don't know if it'll make it, fit better, but it will definitely help it make it a better fit. So again, just be cautious of using the modification indices, but lots of folks use it to make the model fit the data better. So now I want to talk a little bit about best practices. So it is very rare that you'll see in a published paper using structural equation modeling just one model reported, right? You won't just see this model reported here, right? Kind of at the heart of structural equation modeling is the ability to look at different models and compare those models to one another. So usually what we do is we construct other plausible or alternative models to compare our main model to. One way that we can do this is by constraining paths. So we can constrain a particular path in our model to be 0 or some other value. We can also constrain paths to be equal to one another. And then we could perform a model comparison test to see which one fits the data the best. Additionally, we can just assess an alternative hypothesis or model. Maybe we have some idea of a model that contains a variable that the original model doesn't even have that might fit the data better. So using our original model, what we can do is we can constrain one of the paths in our model, our original model, to be 0. So what I'm stating here is that the relationship between external pressure and intentions to apply is 0. I'm saying that that path doesn't have any relationship on intentions to apply, and we don't need it in the model. What I'm highlighting here is how we can do that. So basically, we're just using the main model syntax that we fit before, and I can specify, just using 0 here and the asterisk symbol, that that path be 0. So by putting 0 here, I'm saying that that path is not important, or that path is zero essentially. Then what we can do is we can fit our model, which I'm doing here with bootstrap samples, and then we can compare the models to one another. So this is an example of a nested model comparison where we're taking a more complex model and then subtracting a parameter from it. And because we're doing this, it's a nested model. And what we want to do is we want to evaluate the model fits for both models first. So we want to make sure that both models fit the data well. If one sucks, you go with the least crappy one, so the one that fits the data well, but if both suck, don't compare them. But when we fit the models and they both have good model fit indices, what we could do is we can use the LRT test, the likelihood ratio test, to compare those two models. So what I'm highlighting here is the performance function, or the performance package compare performance function that will basically fit both of our models, and it will output all of the fit indices for both of our models. So we can compare to see if our models fit the data well. That's the first step. And we can see that both models have non-significant chi-square tests, right? The p-values are not statistically significant. We can look at the CFI statistic here. They're both 1, so that's good. The RMSEA is 0, that's good. The SRMR is less than 0.08, and that's the same for both of them, so it's less than 0.08 for both of them. So both models fit the data pretty well. So because both models fit the data pretty well, we can conduct a change in chi-square. And we can use the test likelihood ratio function that we've used before to test models. And I want to note here that when we constrain a model, right, so we set a path to be 0, that frees up 1 degree of freedom. So the most parsimonious model in this case would be the one that has the most degrees of freedom. So when we conduct the likelihood ratio test here, we see that our p-value is not statistically significant. So what do we do with this information? We use the most parsimonious model, right? And that would be the one where we constrain that path to be 0. So it has more degrees of freedom. So this is the model where we've constrained the path from external pressure to intent to apply to be 0. So we would go with that model using this model comparison approach. So that's an example of a nested model comparison. We could also do non-nested model comparisons. So this would be an alternative hypothesis or model that we fit with the data. So I have that highlighted here, right? This is our original model that we're fitting. And this is just an alternative non-nested model here, where you see that now we just have job opportunities directly affecting actual behavior. And then we have perceived value predicting intentions to apply, and intentions to apply predicting actually applying to grad school. So a simplified model, but it's a non-nested model because we're including a variable that's not included in our original model. So what I have highlighted here is just some sample syntax here of how we could fit the non-nested model. And essentially what we would do is we'd have to make sure first that the models fit the data well. And if they do, we would compare the models with AIC or BIC. So we can't use chi-square. Chi-square tests are usually used for nested models. But we can use AIC or BIC and go with the lowest one to determine the best model. And we could do that by using the compare performance function here. And I just have some sample syntax if you needed to do that. So this is an example of a nested model write-up. So I'm not going to go through that. And then this is an example of a non-nested model write-up. So how you would explain these type of things. So now I want to talk a little bit about some practical issues associated with structural equation modeling. And one of those issues is sample size. So how many individuals, how many people do we need in our structural equation modeling? And unfortunately, there's not an easy answer for this. You'll probably need hundreds of people to actually perform structural equation modeling. So I've included some references if this is something you're particularly interested in, if you're thinking about performing structural equation modeling. I've included some references. And then Greg Hancock came a couple weeks ago, and I linked to his talk here. And he came up with a very, I think, genius way and a very easy and simple way to calculate power and sample size in path models and structural equation modeling. So if you're interested in that, I would definitely go look at his talk. But it seems like a very, very intuitive, simple way to figure out the power and how many people you need. But generally speaking, you probably need hundreds. So there is a sample size rule that some folks use called the NQ rule, where N is the number of people and Q is the number of estimated parameters in our model. So ideally, we want 20 to 1. 10 to 1 is acceptable, and then maybe even 5 to 1 is acceptable. But again, we need lots of people, unfortunately, to test these relationships. So I wanted to talk a little bit about assumptions. So pretty easy. All the assumptions that underlie linear modeling and regression underlie structural equation modeling. So things like linearity, heteroscedasticity, normality, all apply to structural equation modeling. So obviously, if one of those assumptions are violated, we can do some corrections that we went over. What's commonly done is the use of what are called robust estimators. So one popular one that's used in the structural equation modeling world is the Satora-Bettler estimator. And I just have some sample code here where if you wanted to run a model with the Satora-Bettler estimator, you could just set tests to this and you'll have robust estimation. So if you have non-normality in your data or you have heteroscedasticity, you would probably want to set something like this. All right, so that was a lot. I threw a lot at you guys. So again, everything that I say is not meant to just kind of seep into your brains and you're expected to know everything, right? So what I wanted to do with this lecture was just introduce you to structural equation modeling so you'll know when you should use it and maybe when you shouldn't use it. And also I wanted to give you some starter code. So if you wanted to perform structural equation modeling at some point in your career, you'd have some code, you'd have some basis to build up from. But in a nutshell, structural equation modeling is this umbrella term that constitutes things like path analysis and factor analysis, which we'll talk more about next week. And this allows us to model observed variables as well as things that don't exist, latent constructs. It focuses heavily on model fit to evaluate how well the proposed model fits the data. And this is essentially lies at the heart of structural equation modeling. We want to compare different models to one another and see which one best fits the data in our theory. And then it's also very flexible. So there's several variations, extensions, and applications to structural equation modeling. So you'll be happy to know that there's going to be no lab on Wednesday. So yay, I know you're all excited about that. However, I'm going to incorporate structural equation modeling into the lab next week. But I will be here on Wednesday. So if you wanted to work on whatever you want to work on, if you want to work on past labs, maybe addressing some of my comments or feedback, I will be here. If you want to talk about your own personal research and ask me questions about that, I'll be here for that too. So it could be like a little office hours. It's open. Next week, DT and Brooke, who are not here, we'll talk about factor analysis. So they'll introduce us to factor analysis. And then what I wanted to announce is that there's going to be a free structural equation modeling workshop, May 8th to 10th. And that's going to be hosted by Patrick Curran and Dan Bauer. And it's a free workshop, and it's going to be, I think, pretty good. And I've included the link, so if you wanted to sign up for that, and if you're interested in structural equation modeling and you want to learn more, I think this is going to go more in depth. Obviously, it's over multiple days. I've kind of tried to shove everything into one lecture. So again, if you want to go more in depth into structural equation modeling, I definitely would, sign up for the free SEM workshop. Dan Bauer and Patrick Curran are kind of experts in the field. So I think that they'd be better able to teach you structural equation modeling than me. That's not at Princeton. It's all online. It's virtual. I wish it was here. But yeah, no, it's all online from the 8th to 10th. All right, so that is all that I have. Are there any questions, comments about structural equation modeling, path analysis, life? Yeah. Yeah, there is. So there's multi-level structural equation modeling called MSEM. Yeah, so it can get pretty complex. So we did have a talk by Keenan Joyner were you at that one last semester? Where he talked about multi-level structural equation modeling, and he looked at physiological data. I can't remember if you were there or not, but he talked about it. Yeah, so there's lots of extensions to this. Yeah. But yeah, there's multi-level components to all of these complicated techniques. So you could do multi-level factor analysis, multi-level structural equation modeling. It's insane. So he did everything in M+. So I think the functionality of Lavon is pretty limited when you get more complex, like multi-level structural equation modeling. I think it could do simple models, but not if you're going to do something really complex. So that's all that I have. So you guys are free to go. Chris, do you have any questions if you're still there?
I'm still here and I do not.
Okay, awesome. All right. Maybe I'll see you on Wednesday, but if not, I will see you next week.